We will listen now an invited lecturer, and it's Professor Carlos Rinaldi that will be talking. He's a specialist in laser ablation-induced spectroscopy. This is LIBS. Molecular beams and isotopic separation with experience in the development of prototypes for laser and micro machining and electronic nodes for environmental applications. He's a CONISTET researcher. He is professor at the School of Science and Technology of the Universidad de San Martín, and he works as researcher in the Fundación Argentina de Nanotecnología. Please, Carlos.
Okay. Thank you to the conference programming committee for giving me the opportunity to present this work, and thanks to Dr. Boykens, we can give me the confiance to present this. Okay. 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 Well. The space exploration gives us a wonderful picture. Many of you could see many pictures of this in the television, of course. And the space is a great source of business opportunities, especially for some enterprise, that can offer the possibility to fly to the moon. If you have the money to go there, you can take up a ship to go there. But also, it is necessary to use the same equipment to send satellites at the space. This is an interesting use of the ship, but okay. The rockets, when you send the rocket at the atmosphere, they produce or they use a conventional and toxic propellants. And this is an important issue because in the future, probably, I think, we have a lot of ships that are going to the outside, and they probably produce toxic propellants. And this is an important issue because the annual scientific assessment for the destruction and the ozone layer introduced for the first time this problem. And also the UNIT National Environmental Program and the World Health Organization put this item for investigation in the future. There are scarcely investigation in this problem. And we think, and I think, this is a very important issue in the future. Okay. The other issue is the satellite propulsion. When you put a satellite in the orbit, you need a rocket. But this is one of the problems. The other problem is how the satellite is flying near to the Earth, and how you can position the satellite. You need fuel to move the satellite between different orbits. When you put the satellite in the orbit, you have a stationary orbit, and you can change using different quantities of fuel. Also, okay, you can see. The satellite don't need a special aerodynamic design because in the space you don't have resistance, yeah, and you need a very small quantity of fuel to move the satellite or orientate it or to control the satellite to see at the Earth. And when this fuel is how do you say exhaust, the satellite can't move anymore. And this is to produce space debris. And it is important that this space debris, what we do with that? at this time, there are a lot of satellites orbiting the Earth, with constituting a very high space debris. It is possible to go down using laser ablation, and it is important also the type of fuel that they use for the control the satellite. Okay. This is the problem. The problem is what we do with this problem. We always think solving the problem in any way and with anything. But first, when you arrive at the solution, then you ask, is the solution pollute or not? If the solution pollute, you need to study a way to solve this another problem. And our proposal is, we know that the laser propulsion for satellite is a well method to control the satellite. And we need to measure the figure of merit, call it coupling, I forget the name, excuse me. Coupling coefficient and impulse coefficient. These two issues are very important for the fuel. And the most important thing is what's the material that we use to produce these propellants. And if you use propellant that contaminant or are not eco-friendly, you need to use another one. But this is our proposal. Okay. If we think that we try to solve the problem with this method, we propose a procedure to use laser propulsion with elements that could be eco-friendly. But before to look at the method to prepare this type of fuel, I want to explain what about the laser propulsion is. And here, let's talk about a very short history about the laser propulsion. Then I will talk about properly the laser ablation propulsion, which is the figure of merit that we need to characterize the propulsion propellant, and our idea of how to use this propellant in the satellite propulsion. The first topic that is research that work in this field was proposed by Arthur Kantowicz in 1972. They proposed that it's possible to replace the chemical propulsion by laser ablation propulsion. The thing that the power of the plasma can replace the power of the chemical reaction. And in the last 50 or 20 years, I think, the laser technology has increased. Nowadays, we have diode laser and also fiber laser with high power and really very small. And in this sense, it is possible to use this type of laser for laser propulsion. Also, in October of 2000, yes, Lake Mirabeau, a research of the Polytechnic Institute, they made a very interesting experiment that put not in the space, but at 71 meters, and a spacecraft, the dimension of 12.2 centimeters and 50 grams, and using a high power laser of 10 kilowatts, an infrared laser. Okay. With the use of the new laser, it is possible to obtain a very good laser propulsion. Here we have an image of the spacecraft produced by Mirato, and you can see the form of the spacecraft, and I can show with the laser. Okay, so here it is. Yes, the problem of this design is that the laser attenuation according to the distance, go down according to the law, the big law. And we can focus the laser in this point, yes? The laser go at this, reflect the laser beam here, and it's focused in this point. This point produces the plasma, and the spacecraft is ejected. But when you reach to the 70 meters, the atmosphere go down the density, and also the intensity of the laser go down, and the plasma is on down, and the flat is go up. Okay, there are at least 3 types of mechanisms for the laser propulsion. One of these is gas-solid propulsion, which is my specialist, and the other is plasma using gas for produce the propulsion. And in any case, you can use laser, pulse laser or continuous wave laser. The last one is the femto laser channel, but this type of propulsion is out of the scope of this talk, and I will talk about the first one. Here, we present how is the, okay, like that. This is the process of the laser propulsion. This is okay, that's. Well, I try to explain this figure. When the when the laser is over the surface, it produces first an electron emission. Then we have acceleration of the ion, and it produces a Coulombic explosion. And then it produces a very high evaporation, an explosion. And you have evaporation of the surface because the surface reaches near to 40,000 Kelvin in temperature. And the velocity of the ion is very high. Look at this. This is our first experiment. We think that if you use the laser over the surface, we can move anything. But we do this experiment in our laboratory. See at the flash, please. Oh, again, please. You see the flash? Okay. And this produced a movement. Take into account that this was performed in a laboratory with a typical CO2 laser with 1 joule of energy per pulse, and we can move this object with near 5 grams. Yes? And it's in the air. Okay, the velocity of the ion here, you can see, this is a typical behavior of the ion ejected from the surface. The left hand, you can see the typical Maxwell-Boltzmann distribution of the neutral species, and on the right hand, you can see the same distribution, but for ion. The ion velocity is higher than the neutral atoms. And the typical velocity of this ion is near to, for the barium, near to 20 kilometers by second, for the magnesium 50, and for the calcium 40 kilometers by second. We can dimension the value of the velocity, but suppose that you forget, Assam, the USB in your house, and you have to keep there, but your house is 20 kilometers from here, and call your wife and say you forget the memory. Okay, in 1 second I can reach to my house, and in 2 seconds I can come here. That's the velocity of the atom. Also, we can compare with Formula if one car. This is a 0.1 kilometer by second. And we drive our atom at 25 kilometers by second, but we get money 1 million of less than time. Oops. Okay. The other mechanism to use is the plasma sustain. In this case, you need a flow of gas in the chamber, and the laser comes from this point and produce the plasma in this point. You need a chamber for this system. And when you produce the plasma, here you get the propulsion in this point. But the problem in this system is that you need a special flow velocity, and also you need just the energy enough to produce the plasma. It's very unstable, the plasma here. And if you change the velocity of the flow, or you change the laser intensity, the plasma sustain is down and you lost the propulsion. This is a problem of this type of propulsion. Oops. Okay, we need here is the scheme of the laser propulsion. This is the spacecraft, and this is the atom coming from the fuel. And we need the momentum conservative law, and the velocity, the change of the velocity for the mass will be equal to the velocity of the ion for the velocity. And this is a very high mass, but low velocity. And we have here a very high velocity and low mass of the jet material. And we need to measure the change of the mass in this system. For this reason, we use a system which is called, this is, okay, this is, yes, well, okay. This is not my computer. Okay, this is a scheme of how it works, then the laser, and you see how this produces the impulse of the surface. Please, look at this video, and look at the flash near here. You see the flash? And you see how move the pendulum? Please, again. Okay, that's, here is, okay. Well, we need to measure how is this movement, and we develop in the system, and we use image analysis system using a program called ImageG, and we can take the movement here. This is the angle between the arms of the pendulum and the laser, and you see this is the angle, and here it is possible to obtain the different position of the pendulum during the movement. Please. We can do this automatically, and we can get the information of the velocity of the pendulum and from different movements. We can take this in many times, and we can average many of these measurements. We see that this is a typical harmonic attenuation of the harmonic oscillation. This is as a function of the time, and we can here measure the angular velocity, which is direct. Give us directly the coefficient, the coupling coefficient, and we can obtain how efficient is our propellant. No? But we need also to obtain another issue is the impulse coefficient, because if you want to spatialize the propellant, you need now with high precision the velocity that you can obtain when you use different lasers. And we use this system, which is a Normansky interferometric system that we would improve using two lasers. This is the ablation laser, and this is the reader laser. And we obtain here the interferometric measurement, and as a function of the different interferometric image, here is the typical image, we can obtain the velocity of the ion. And with this system, it is possible to get a very high precision in the velocity, and also we can qualify our fuel. This is very important because we talk with different satellite producers, yes, and they ask for, we need to give him a very good precision of our velocity, and also which is the difference between pulse to pulse when you put in movements the pendulum. Okay, this is our result when you use this type of propellant. We prepare a carbon-calcium calcium carbonate mixture with zinc methyl in this proportion. And here you can see how is the coupling coefficient as a function of the zinc quantity. And in the left hand, you can see when you use infrared laser, and at right, you can see the propulsion when you use a UV laser. This is different depending on which laser do you use to produce the propulsion. In this case, our propulsion is better than, with infrared laser, is better than UV lasers. The mechanism of the propulsion is different, it depends on the wavelength of the ablation. And this is our impulse specific measurement using the Normansky measurements, and we can obtain the same as using the pendulum measurement. And the important key here is that the laser ablation propulsion initiates at this point, near to 500 seconds, taking into account that the chemical reaction for laser propulsion, the maximum impulse is 500. Okay? And we initiate where the chemical finish. No? We can obtain a very high impulse with this type of propellants. But we need to study the thermodynamical properties of this type of mixture, because different components can give us different coefficient of propulsion. See here, we have the melting point of the calcium carbonate and the melting point of the zinc. And this is a graph where you see the material ejected from the surface as a function of the fluent of the laser, and it depends on the enthalpy of the carbon calcium. And this is very important because it not depends of the metal. And we can use the metal as a cohesive system and use the energy of the calcium carbonate as impulse material. When you use another type of compound, like nickel or sodium fluoride, you have these thermodynamics properties. Yeah, this is a very high temperature, also for the sodium fluoride, and if you measure the material ejected from the surface, you can see for the metal here, you can see for the metal low emission, for the sodium fluoride a high emission. But if you make a mixture between the metal and the salt, you can obtain a compound that has the best property of the metal and the best property of the fluorine iodide for propellant. Yeah? But we need to study which is the best mixture, the best percentage. Yeah? Well, our procedure is Then, for satellite propulsion, well, we need to measure, we need to use the laser propulsion, and we need to measure the coefficient coupling, the impulse coefficient. We need to know the laser power and also the efficient, how the energy is transferred to the propellant. And then we need to select the material. That is the best important key in this process, because we use this type of material, we can get a very high couple coefficient, but the system is not eco-friendly. And we can use this one, zinc or calcium carbonate. You have a low propulsion, but it's eco-friendly. Also, is have a propulsion better than chemical propulsion. No? Oops. Okay, this is our process that we propose in order to develop material for laser propulsion. First, we need to study the thermodynamic measure for the different possible material, and then it need to make the preparation of the possible propellant. After that, it's necessary to measure the different properties of the mix, and then it's necessary to evaluate how if it is convenient or not for the environment. Now? Okay, there are another system for propulsion satellite that this is a MEMS, it's a micro electromechanical machine system, but they use a very small chip, see here, but you need for this system a chamber. In the case of the laser ablation, we don't need this chamber. We use directly here, because in the laser ablation, the propulsion is produced in this point. But when you use a chamber, you need this space and also this. But this system had a drawback that you need to put some fuel that maybe could be contaminant, and also is a one-shot use. You use this one time, and you need to put in the satellite many of these chips in order to produce the movement of the satellite. This is another type of MEMS that is currently work, but have the same problem as mentioned before. And then, this is our proposal for use in satellite. Here, we think to put here our machine, our propulsion here, and we can move the engine, see, in this angle and the other, and it is possible to move the satellite in any sense, you know, in any orientation. And also it is possible to change the orbit of this type of satellite. The object of this research is to use this type of propulsion in micro and nano satellites from 1 to 10 kilograms, not for bigger satellites. Yeah? Well, this is the end, and yesterday at the end of the very nice reception, it was a Tango school, and we have a winner, yes. Maybe this is the school, and we have here is the professor, but I don't know who was the winner. You can select one. I suppose it was Ingo, that here. It was dancing well. Yeah, okay. That's all, and many thanks for your attention.